morning, everyone. Thank you for your attention. I'm our presenter Nami Ha, a PhD candidate from the Department of Mechanical Engineering at Pohang University of Science and Technology. In this presentation, I'm gonna introduce the water transport strategy of plant genus Tillandsia. Have you observed these kinds of epiphytic plants? This presentation aims to explore how these air plants could effectively get water for their survival. This plant is the genus Tillandsia among epiphytic bromeliads that absorb water and nutrients from their leaves or stems from rain, fog, and dew. Among Tillandsia species, we investigate Tillandsia osneoides that hangs on other trees under the tropical or arid regions. Tillandsia has no absorptive roots for water absorption and has narrow vascular bundles with the tracheids of the diameter around 6 to 8 microns, which implies very slow flow speed. Instead, they develop hairy trichomes on the shoot surfaces to enhance the absorption of water from atmospheric sources. Many researchers investigated this fascinating water management strategy of Tillandsia. However, most of the studies focused on the roles of trichomes on water absorption and the prevention of water loss. A few studies asked a question on whether the traditional vascular transport would be a dominant transport way compared with the external capillary flow, but how the Tillandsia can transport water rapidly is still unclear. In this aspect, we try to reveal the water transport mechanism of Tillandsia by focusing on the role of trichome wings. Trichome comprises two parts, shield and stalk. The shield is composed of dead cells, wing and central shield cells, while the stalk consists of living cells, dome and foot cells. Here, our focus is to investigate the effect of wings on the external water transport. First, we analyze the morphological features of trichome wings. As shown in figures, there are some parameters such as wing length, interval distance between trichomes, wing thickness, number density of trichomes, etc. These factors imply three facts. First, the ratio of wing thickness over length much smaller than 1 means very thin wings. Second, the ratio of the trichome interval distance over the wing length around 10 to the power of -1, and the high trichome number density indicate the densely distributed wings. In addition, the wing length is around 300 microns on average and is 10 times smaller than the capillary length scale. When we observe the cross-section of trichome wings, wing cells have thick walls and cavities inside the walls. Moreover, the lower walls are thinner than the upper walls, suggesting that the lower walls could be deformed much easily than the upper walls. We further observed the wing-ring connection regions through X-ray microcomputed tomography. The ring cells comprise ring 1 and ring 2. In contrast with ring 1 and the central disc cells, where the thick walls rigidly connect, ring 2 and the wing cells form a relatively thin joint. It suggests that this joint might act as a hinge upon which a restoring force applies when the wings deviate from their initial state. Second, we investigated the wettability and elasticity of wings. The contact angle value of a droughtlet on the intact Tillandsia was nearly zero due to the enhanced roughness by densely distributed hydrophilic wings. On the other hand, the contact angle on Tillandsia without wings was about 106 degrees, which attributes to the waxy cuticles and the relatively low roughness due to the absence of wings. The Young's modulus of the wing was derived from the approaching contact force measured by atomic force microscopy, and its value was the order of 100 megapascal. Assuming a cantilever under a single load, the bending stiffness would be 10 to the power of minus 10. Given the bending displacement of 100 microns, the ratio of capillary force over the elastic force will be 10 to the power of 2. Moreover, the electrocapillary length at which the surface energy is comparable to the bending energy is 37 microns. These simple scaling show that the wings with a length scale 6 times longer than the elastocapillary length would be sufficiently deformable by the surface tension of the water film. In other words, the pulling force of the water film would not reconfigure the wings if the wing lengths were shorter than the elastocapillary length. Based on the observation on the morphology of wings, we visualize the external water transport. As shown in the movie, the fluorescence intensity varies as a thin film of water propagates on the intact Tillandsia surface, while it does not vary on the surface without wings. In other words, no wings, no film transfer. This external transport across wing arrays will be advantageous for Tillandsia by considering the entangled propensity in nature. Then, what about the detailed transport process? Contrast-enhanced X-ray images show the film propagation in detail. During the wetting phase, the wings were flattened according to the propagation of the water film. Later, the wings returned to their original positions due to the absence of the water film during the drying phase. In other words, the surface tension force of the water film pulled the wings to be deformed, which in turn increased the wet length and made the neighboring wings wet. This phenomenon was also observed during the fog and dew conditions. For instance, under the fog flow condition, you could see that the rising water film deflects the wing. Here we call this phenomenon as reconfiguration of wings by the water film. According to the water absorption into the trichome, the elastic force works on the wing to recover the original configuration of wings. Based on the wing reconfiguration, we can explain the mechanism of external water transport across flexible wings as 3 steps: propagation of a thin film of water, flattening of wings, and water transport to neighboring wings. As a result, we integrate the roles of trichomes on water management. First, the trichome wings enhance the spreading of the water film flow by accompanying sequential flattening of wing. Second, as revealed by other researchers, the high water potential gradient across the semi-permeable membrane of food cells allows water to be rapidly absorbed into the plant tissues. During the process, the wings recover the initial position. Finally, the cavities are filled with an air again, which prevents water loss by means of shifting the liquid-gas interface inside. Tillandsia repeats these sequential cycles to harvest water with the aid of reconfiguration of wings. Noting the film flow across the wing arrays on the Tillandsia surface, we perform the capillary rise experiment to quantify temporal variation of wet length in a macroscopic view. As a result, the wet length collapsed onto a single straight line with a slope of 2/3, which was different from the conventional capillary rise proportional to square root of time. Tillandsia's surface could be modeled as a superhydrophilic structure with hydrophilic shield arrays on the epidermal substrate. Thus, if we assume the wings are rigid structures, the fin would propagate with a scaling law of length proportional to the square root of time by balancing the capillary force and resisting viscous force. However, the wings are not rigid structures but flexible ones, which allows the water film to pull the wings and make them flattened. In other words, the area of the air-water interface formed by the water film, wings, and epidermal surface decreases to reduce the surface energy, whose cost comes from increasing the elastic energy arising from wing deformation. In addition, as wings are porous hydrophilic polysaccharides like cellulosic paper, and thus the flexibility further increases with being wet. Based on the experimental results, we compare the external water transport velocity to the internal velocity. As water transport on the Tillandsia surface collapsed onto lengths proportional to 2/3 power of time, the transport distance satisfies this empirical equation. Thus, the fin flow follows this velocity equation, and the velocity is scaled as like this. Theoretically, from the fully developed Fuzzy equation, we could derive the internal velocity through traces with a diameter of 6 to 8 microns. As a result, the external and internal water transport velocities are order of 10 to the power of -4 and -5, and order of 10 to the power of -5 and -7 respectively. It suggests that trichome-mediated transport on the Tillandsia surface has a higher order of velocity than the internal vascular transport. To identify whether the flow speed in vascular bundles has a value similar in the range of the theoretical scaling, the dynamical motions of tracer particles in the set flow were observed using a contrast-enhanced X-ray imaging technique. Gold nanoparticles of 200 nanometer in average diameter were selected as tracer particles. By assuming the diameter of tracer particles as the size of aggregated gold nanoparticles, about 3 microns, the characteristic time of particles in the traces is 10 to the power of -8 seconds. As a result, the speed is estimated to be 6.53 microns per second, being consistent with the theoretical scaling. Accordingly, the Stokes number is 10 to the power of -9, which indicates that the gold nanoparticles closely follow the fluid streamlines. These results support that the external water transport through the trichome wing arrays induces much faster water transport compared with the internal vascular flow. In conclusion, based on the hypothesis that Tillandsia rapidly transports water via trichome wings rather than via the narrowed internal vascular bundles, we found 3 facts. First, peltate trichome wings are flexible enough to be deformed by the surface tension force of the water film. Second, sequential flattening of porous hydrophilic wings increases the wet length in a domino-like manner at the cost of increasing the elastic energy at the wing ring joint. And third, Tillandsia repeat ring reconfiguration in a water harvesting cycle, leading to sustainable and effective water transport via trichome wings. This is the end of my presentation. If you have any question or comments, please feel free to ask me any question. Thank you for your listening.